In summary, when given a complex number expressed in rectangular format with a real x and imaginary y component, one determines the magnitude z of the polar as the square root of the sum of the squares of the real x and imaginary y components, and one determines the angle theta as the inverse tangent of the imaginary y over the real x, taking into account positive rotation is defined as counterclockwise and negative rotation is defined as clockwise, as well as active intervention for those values in the second and third quadrant. Let's try some illustrated examples of a conversion from rectangular to polar. Let's try some illustrated example problems of conversion from rectangular to polar format. Given a complex number a, expressed using rectangular format as 3.1 plus j 4.7, let's express it using polar format. Note we're in the first quadrant, and we should expect an angle between 0 and positive 90 degrees. Let's determine the magnitude first. One determines the magnitude as the square root of the sum of the squares of the real x and imaginary y components. Substituting in our given values, we find a magnitude of roughly 5.6. Now let's determine the angle. One determines the angle of the polar equivalent as the inverse tangent of the imaginary y over the real x. Substituting in our given values, we find an angle of roughly 56.5 degrees. 3.1 plus j 4.7 in rectangular format is roughly equivalent to 5.6 at an angle of 56.5 degrees expressed in polar format. Here's another illustrated example of conversion from rectangular to polar format. Given a complex number expressed using rectangular format as negative 5.2 minus j 5.2, let's express it using polar format. Note we're in the third quadrant, and we should expect an angle between negative 90 degrees and negative 180 degrees. This will take some active intervention on our part to format the angle as we desire. Let's determine the magnitude first. One determines the magnitude of the polar equivalent as the square root of the sum of the squares of the real x and imaginary y components. Substituting in our given values, we find a magnitude of roughly 7.4. Now let's determine the angle. One determines the angle of the polar equivalent as the inverse tangent of the imaginary y over the real x. Substituting in our given values, we find an angle of positive 45 degrees. This is totally wrong because we're obviously in the third quadrant. Referencing the angle from the positive x-axis by subtracting 180, we obtain an angle of negative 135 degrees. Negative 5.2 minus j 5.2 in rectangular format is equivalent to 7.4 at an angle of negative 135 degrees expressed using polar format. Put your understanding of converting from rectangular format to polar format to the test with these example problems. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. For our first example, positive 4.9 minus j 7.3 is equivalent to 8.8 at an angle of negative 56.1 degrees. Note rectangular format places us in the fourth quadrant, and our resultant angle is between 0 and negative 90 degrees, as we'd expect. For our second example, negative 3.3 plus j 8.6 is roughly equivalent to 9.2 at an angle of 111 degrees. Note rectangular format would place us in the second quadrant and necessitates active intervention on our part to arrive at an angle between positive 90 degrees and positive 180 degrees as we'd anticipate. For our third example problem, 4.0 plus j 7.5 is roughly equivalent to 8.5 at an angle of 61.9 degrees. Note rectangular format would place us in the first quadrant, and our resultant angle is between 0 and positive 90 degrees, as we'd expect. For our fourth example problem, negative 4.3 minus j times 2.7 is roughly equivalent to 5.1 at an angle of negative 147.9 degrees. Note rectangular format would place us in the third quadrant and necessitates active intervention on our part to format the resultant angle between negative 90 and negative 180 degrees as we'd anticipate. The last example problem is a little tricky. Expressed using rectangular format, it's negative j 5.6, meaning it has no real components, and the entire complex number can be expressed as a single imaginary component in the negative vertical direction. If we were to express this using polar format, using a magnitude and an angle, that's quite obviously has a magnitude of 5.6, pointed at negative 90 degrees. Negative J 5.6 is therefore equivalent to 5.6 at an angle of negative 90 degrees. Alright, that's about enough for today. We'll examine the means of converting from polar to rectangular, more math functions with complex numbers, and the use of scientific calculators in later lectures. In conclusion, this lecture presented the means of converting complex numbers expressed using rectangular format into an equivalent complex number expressed in polar format. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.